So the facility behind me here is the Chrysalis. That's one of our proudest accomplishments, at least so far. It'll be the world's largest medical isotope production facility. We believe we'll produce more doses of medicine out of this facility than any other in the world, and believe its capacity is up to about 20 million doses of medicine every year. Second, I think it'll be the first major beneficial use of fusion to benefit humanity on a massive scale. Over its lifetime, we expect to produce 1 billion doses of medicine out of here, and it's certainly an incredibly positive use of fusion, and we're really excited to be bringing that value to the world as we're on our stepwise path to fusion energy. And finally, I think it'll be probably one of the most versatile sources of neutrons in the world. We call it the chrysalis because a chrysalis is this state of transformation in nature where a creature that's typically considered not all that beautiful is turning into this beautiful creature like a butterfly. And one of the things we do in this facility is we take material that was once intended to be part of nuclear weapons, or actually was a part of nuclear weapon, and turn it into medicine. But it also is relevant because in the chrysalis state, this creature is essentially impregnable, right? It's this hardened shell. It's protected against nature while it's in its transformation. As you go through the inside of the chrysalis, it becomes obvious that this building also has that characteristic. It has 2-foot thick concrete walls with massive amounts of rebar, and it can withstand an airplane crash, can withstand an F5 tornado. It's a hardcore nuclear facility, 10 CFR Part 50 licensed facility. To my knowledge, we're actually the first growth stage company or sooner to ever build something like this. So here we are inside the chrysalis. The chrysalis has really 3 primary areas. What we're standing in is called the non-safety related annex. The building construction around us right here is actually standard construction. As you go inside to the hardened area, you can see this thick wall here. It's about 2 feet thick. That's the protected area, so that's where the radioactive material is, the medicine that we'll be producing over time. So coming down the corridor of the non-safety related part of the facility, first we're going to see the electrical switchgear where electrical power comes into the facility. The challenge with a facility like the Chrysalis when you're building things up to nuclear codes is they can be really difficult to upgrade down the road. And so we try to be really thoughtful with it. Anytime we had conduits, we multiplied by 2. Same with wall penetrations. Anytime we needed a hole in the wall, we multiplied by 3. We expect it to improve in time, to go to higher output, higher flux, and higher capability. So we wanted to make sure the building could support that as the technology emerges. So walking down toward the hardened facility, this is actually where most plant employees will enter. There'll be radiation portal monitors checking them when they come in and when they leave to make sure they're not bringing in any contamination or taking any out. If you just look at the wall here, this is sort of standard drywall sheetrock construction, and this is concrete. So we've now traversed from the standard construction to the nuclear facilities. So now we're coming into the control room corridor, and this is where the general facility operators for the whole plant will be. We're passing a couple of rooms here where we'll actually have battery backup supplies. People who are used to thinking about nuclear power plant control rooms are used to like big green panels with lots of buttons and switches. What you'll see is actually this. This is the actual control room equipment being mocked up at the vendor. So very modern in the sense of what we're doing with nuclear technology here. So now we're heading from the control room corridor into what we call the RPF, or the Radioisotope Production Facility, which is where we take isotopes that we've produced with our fusion-based process and we separate them out to medical grade purity. So you can kind of get a sense of the scale of a place like this. As you come in, you look up, you look around you. All of this is part of the hardened facility. On the other side of that wall, our fusion systems sit that produce the medical isotope. So it's producing it in a uranium solution, and it essentially comes over to this side of the building. And so down here where you see all these open vaults, there's piping that can move solution back and forth across the facility. And there are various tanks that can hold that solution, that radioactive material that we're making isotopes in. The goal is to provide interconnectivity through this piping that goes in the middle, and what will eventually be installed over here, which will be our hot cells. So hot cells for the facility will be installed sort of in this area where you see blue tape. They'll fill that area. And the hot cells are where we essentially purify isotopes that we want for medicine to medical grade at enormous scale. One of the key hallmarks of this plant is a really large vault where we keep a whole bunch of carbon, essentially carbon air filters. We're actually trapping any radioactive byproducts that might go out the stack until they decay in these really large carbon delay beds. And you can actually see the vaults for those here. And that makes sure that all situations, plant emissions are well below regulatory limits. All waste from this facility will leave in solid form. This is actually the area where a lot of the magic happens. This is where we produce the isotopes. Each of these vaults, as I mentioned, there's 8 different vaults we can use for isotope production. Each one of these can produce just a huge amount of isotopes. One of our big advantages over sort of aging research reactors is that if we have a unit go down for maintenance or unexpectedly, we still have the other units continuing to operate and continuing to produce isotopes. We can also tailor our radiation schedule for most efficient delivery to our customers. There's actually another cell just to the right over here. That's actually a test cell. So we can take a production system that's not behaving properly from one of these units, and we can actually use this overhead crane here, pick it up right out of that production cell, put it into this test cell, and we can do more work on it. The idea is that you would replace it very quickly with a new standby working system and get that system back into production as quickly as possible. We're confident this place will still be producing isotopes 50 years from now. So we've now traversed the wall again and are now in the non-safety related part of the building. You can see there's still some construction going on up here. It's actually really important to do air handling really well here. Due to the radioactive nature of our products, it's not just heating and cooling the building, but it's maintaining the right pressure differentials to ensure that you're always blowing from the lowest contaminated areas into the most contaminated areas if anything were ever to go wrong. So all of that is here, and that is essentially the end of our tour of the Chrysalis. An absolute long-term key capability for our nation to make sure that patients have the isotopes they need as new treatments continue to emerge.